Okay, let's start now. Hello, everyone. I think we have how many people on? 7 people. That's sufficient to start. So thanks a lot for coming. If you open the chat up, I've posted a PDF file of the notes I made for today's thing. Yeah, it's just a couple of pages, and I'm going to go through first a couple of definitions, a bit about projective geometry before finally finding what an elliptic curve is. Any questions, comments before I start? Oh, Winston's joining.
One question, are we doing it over an arbitrary base field?
The first 2 sections are over, well, the first 2 things I'm talking about will be over arbitrary. Elliptic curves I've defined arbitrarily, but we're going to do everything in Q, since, well, Silverman and Tate's book is labeled what rational points on elliptic curve.
Okay.
Labeled this here.
Mm.
So we can consider the rational stuff first and then figure out what we do after. I guess Lucas is the professional, right? Lucas, you've read all Silverman's books, I've heard, so you could present some of the lecture.
All of them.
Right, yep. Yep, let's make a start. Yeah, feel free to stop me at any time if you have questions, and I'll talk for about half an hour, and we can talk about what to do next week and stuff. So let's go to this PDF screen. Oh, that's my assignment, not that. This thing. Nice. Just working on 720. So I'm gonna do an introduction to the introduction of elliptic curves. So if everyone just maximizes my webcam, you see the notes on screen there, or just look on the PDF file I've sent you. So first of all, definition 1.1 is stuff I always forget. Well, I remember what the degree is. The degree is of a polynomial is the highest degree of all the monomials, and a homogeneous polynomial has degrees of all the same, so all the terms have the same degree. So the first thing I'm going to properly define is what a singularity is. So a singularity, I'm going to use the definition that an affine curve has a singularity at a particular point if the formal derivative at that point is 0 in all variables. And smooth means it has no singularities. Smooth also has about 10 different other definitions. So yeah, beware if you go on Wikipedia or something. So the first interesting proposition, a point is smooth if and only if it has one tangent. And this remark I will do on the whiteboard now, or whiteboard in quote marks. Yeah, so I'm gonna do this probably in 2 variables since it's easier to do, but you can generalize this. So let's take our curve to be some f x comma y, and then write this out, say write kind of each monomial out, though actually I'm going to group all the monomials of the same degree together. So if we let f of x comma y be a polynomial such that I'm going to use this notation, so rk of x comma y plus rn of x comma y. Can everyone see what I'm writing? Just making sure.
Yep, I can see it.
Me too.
Thanks.
Yeah.
Right. So so each term in the sum is a polynomial of degree k, or degree I should say. So each ri has degree I, and it also only contains monomials of degree I. So say if something was x cubed plus 2x squared y, this will be, say, r3 plus x plus 2y. This will be, say, r1, like that. And then rn is the degree of f, and rk is the degree of the smallest monomial in f. Oh, I'm rambling a lot. Okay, let's keep going. So actually, let's consider the singularity at the point 0, 0, since otherwise we can always do a linear transformation to the origin. And so that way we're considering the point p equals 0, 0. And then from here, we know from basic, I guess, calculus or something that at 0, 0, the lowest terms, or the terms of the lowest degrees dominate the polynomial. So we can consider rk of x, y that dominates f at the origin. And then that means we can consider the thing, and this will tell us whether there is a singularity or not. And how do I scroll? I can scroll. Okay. So so say rk has the lowest degree, and that just means the number k kind of defines whether it has a singularity or not. So if k was 1, then it's smooth at 0, 0. If k was 2, then it has a singularity of order 2 or double point. If it was 3, we have a triple point. And you can think of it like rk, we can always factorize by the fundamental theorem as x plus some a, x plus some b plus, times, that should be a times, x plus some variable out here, and there are k terms here, and each one kind of gives a tangent at that point. And that comes to my next point, where we have a smooth point if and only if it has one tangent. This was the remark I talked about. It's probably easier if I go through an example. So let's consider a circle. So example 1.6, let's consider if, so.
Sorry, I don't want to disturb you, but someone wants you to let Dobson in.
Oh, is Dobson? Oh yeah, I should pay attention to that. Can people tell me if? Hello, sorry to leave you guys waiting. I didn't see the entrance room. Welcome. Okay, so I was gonna calculate the singularities of the circle. So this looks like a circle around 0, radius 1. Well, we just consider the derivatives. So we have the derivative of f along x is 2x, derivative of f along y is 2y. These both vanish if and only if x equals y equals 0, and the origin is not inside circle, so we don't have any singularity points. Every point is smooth, and that's kind of obvious looking at the circle. So the next one I wanted to do was x cubed plus x squared minus y squared. Typo in the notes, it should be equal to 0. And this looks like this. And this point is the origin, and just eyeballing the curve, that obviously has a singularity, but to prove that, we just differentiate this. So along x, we have, so if this was f of x comma y, along x, we have 3x squared plus 2x, just basic calculus, 2y, and then we want these both to vanish, so we get, we just will get x equals 0 or x equals 2/3, and this gets y equals 0. 2/3 comma 0 is not on the graph if you check for yourself, so the only singularity is 0, 0. All other curves, all other points on the curve are smooth. So that's what a singularity is. It's not very important for us. It's just to get an idea of when we define an elliptic curve, we want the elliptic curve to be non-singular. So the next thing I wanted to quickly go over was projective geometry. If any of you have done, I guess, any course in algebraic geometry or similar, you would have heard about this. So I wrote to myself some random spiel about the point of infinity. So basically, if we take two lines in R2, say in Euclidean space, then they only, and if the two lines were not the same, then if they were not parallel, they would intersect at one point. If they were parallel, they wouldn't intersect. But we want to force it so that the lines have one point of intersection, even if they were parallel. And that's how we, the motivation of defining projective spaces. So projective space Pn of some random field K just take R or something, is the thing here. So you kind of lift it up one space, take away the origin, and then quotient it by this equivalence relation, which is that it's two vectors are equivalent if they are a scalar multiple of each other. But it's easier to think of it this way. So the projective space is, I don't actually know if it's isomorphic or equal. Could someone help me? I wrote isomorphic because it's always correct to write isomorphic, but it might be equal. It's equal to that original field union the point of infinity. There's random stuff here about lifting polynomials. It doesn't matter too much. It's just the important thing is the Zoo theorem, which is that any two projective curves, so any two curves over an algebraically closed projective field with no common component, that means they don't have a common factor. Well, if the first one has degree m, second has degree n, then we have mn points of intersection counter multiplicities. So grab just an example on a piece of paper. So let's take, so the example I gave before, let's take R2, or actually I should say P squared, it's control Z thing. P squared of R. So two lines intersect at a normal point, but if they were parallel, like this and this, well, they don't intersect in R2, but they intersect at infinity out here somewhere in the projective space. And that's the Zoo theorem saying that we always have at least one intersection between two lines. If we had, say, a circle and a line, the circle has degree 2, a line has degree 1. So there are always 2 points of intersections. And if you have a line out here, this should be C, since we want algebraically closed. So this line out here does intersects in the complex numbers somehow. If it was a tangent, then at this point here, this would be an intersection of multiplicity 2 just by considering limits or something like that, or however you want to define multiplicity. So again, if you are interested in looking at more of this, take a look at Hartshorne or Silverman and Tate, or any your favorite algebraic geometry or number theory textbook. There will be a proof of the Zoo theorem in there. I'm not going to prove it unless someone wants me to prove it in a later session. But let's go on to the fun stuff, which is an elliptic curve. So an elliptic curve I'm going to define as a smooth projective cubic curve with at least 1 point on it. I don't actually know why I wrote with at least 1 point. It was in the definition I looked up. I think it was in Silverman and Tate. But basically, a bit of easy notation. I'm going to define LP of comma Q to be the line between P and Q. That doesn't matter for now. So an example of an elliptic curve. Let's go back to here. Elliptic curve. So an example of an elliptic curve will be something that looks, well, the example I gave earlier, that's badly drawn. This is an elliptic curve. Something that looks like this would be an elliptic curve. Actually, if we just to give you more examples of what an elliptic curve is, well, we want the example on the left is not an elliptic curve since it has a singularity. We want it to be smooth everywhere. So the one on the right will be a elliptic curve. But if we go to here, there's more. So an example of an elliptic curve. So this is not an elliptic curve since it's got a singularity at 0, 0. It's got a cusp there. But something like this is not a singularity. This is not an elliptic curve. This is an elliptic curve. Since this is not a cusp, this is a tangent defined there, and something like this is probably the prototypical example of an elliptic curve. This one, or something like that. So yeah. So I want to, well, why are elliptic curves so interesting to study? Well, I think people find group structure on elliptic curve interesting. So I'm gonna define an operation on the group. Well, I'm gonna define an operation on the elliptic curve and claim that that makes a group. So well, there's this whole thing about it. So let's just draw let's draw this one out since it's probably going to be easier. So let's take an elliptic curve. Say, I am so bad at drawing. Say that looks somewhat like an elliptic curve, and we take one point on the elliptic curve, call that the identity, which I denote by an O, and the sum of 2 points, say P and Q here. Well, we first take I'm going to make the point P bigger. Take the third point of intersection of P and Q, so the line and the cubic, and by Bezout theorem, there are 3 points of intersection. So this point here always exists. Let's call this R. And then we want to do one more line between R and O here, and this would be called the point P plus Q. And the reason why we do this the reason why we don't call R P plus Q is because we want to make the whole thing a group. That's why we reflect it across the identity here. And the inverse of P plus Q would be R, and the inverse, I think, is that how I defined it? Let S be the, okay, so to define an inverse, we take the tangent at this thing, define this to be the point S, and then the third point of intersection between S and P is the inverse. So S and P, third point of intersection is here. So this is the inverse of P. So I claim this operation here makes it a group. Is everyone following me so far? I'll take that as a yes. So I claim that this operation. Yeah. Wait, what was that? Oh, someone's.
Oh, sorry. Quick question.
Yep.
Sorry. Is there if you go back to the drawing?
The drawing. Yep. This drawing, the bad drawing.
Oh no. The one. Yeah. This one. So like, what if like if Q intersects like what if Q and P intersect twice at P? That makes sense.
If Q and P, you mean if Q equals P?
No. If like if you take the line from Q to between Q and P, right?
Take a line between Q and P.
Yeah. You take the line that intersects Q and P, and it intersects the third point R, right?
Yeah.
What if R is equal to Q or P?
Oh right. Sure. So that means the line is tangent. So I'm gonna.
Yeah.
So your example would be, well, this. So if this was P, and this was also R, so it will be tangent like that, right? Is that what you're talking about?
Yeah.
And this was Q. Well, then O would still be here, and you just that should be an O. So this is O, and you would also, well, you take R equals P basically, and then you just
I do the same thing.
You do the same thing. So between O and it's hard to draw. So this will be P plus Q. Yeah.
Right. Okay, cool. Answers my question.
Yeah. So if the point is ever the same, so if we're adding P plus Q, if we're doing P plus Q, but Q is P, so if we're doing 2P, then we take the line tangent at P. So if we want to do P plus P, like if this was O and this here was P, then P plus P would be, we take this line here, this would be our point R, and then we take this here and then it intersects somewhere here, and this will be P plus P. So whenever we have its tangent, we do the thing where, So I claim this makes a group. Well, it's in fact an abelian group. The abelianness is obvious, and also the operation is obviously closed by Bezout theorem. So we have to check the identity. Well, I leave that as an exercise. You could just draw that out, and it's pretty obvious. And also the fact that the inverses exist. The only part is associativity. We won't have time to do that today, but if someone wanted to do that, they could, but it's not very enlightening. It's just a bunch of lines drawn everywhere, and I think it's done case by case. It's like 5 pages in Silverman and Tate or something. I'm talking about Weierstrass form. That's not important, but basically any elliptic curve you can write in this form in Weierstrass form. So you can always do like a linear transformation or whatever they call it in Silverman and Tate. And then we normally, well, I would like to be interested, well, I want to talk about kind of elliptic curves of this form. So y squared equals x cubed plus ax plus b, where a and b are any rational number or something. If we're doing it over q, I would talk about why we use q later. But the reason why we do something like this is because, well, we get rid of every other y term, and if we had an x squared term here, then we can always kind of transform it back into this form just by, I think it's like a linear transformation. So you substitute something into x, something into y, and you get something of this form here. Remember that we want the curve to be smooth. So to ensure there's no singularity, we take the discriminant, this thing here, 4a cubed plus 27b squared, to be non-zero. And normally we also define the identity to be the point at infinity, because this makes things a lot easier. And I'm going to show you why it makes things a lot easier. So back to the drawing. So if we took this curve again, and instead the identity is somewhere at infinity, that means if this was p, then this will be minus p. Since the third point of intersection, well, the third point of intersection of this line and this curve is at infinity. Since these go out that way, these go out that way, so it doesn't intersect anywhere else apart from infinity. That's the third point of intersection. So if this was x comma y, then this would be x comma minus y. So it's literally just a reflection across the x-axis here. So that's inverting, and when you're doing operations, say p plus q here, well, you take the you take the line between p and q. This would be our point r, and you just take the second part of the operation would be taking r and the identity and finding the third point of intersection of that. Well, the identity is at infinity, so again we draw the vertical line, and it will be this point, p plus q. So note that p plus q is minus r, and r is minus p plus q, minus p minus q. Yeah. What's the time? It is almost past, so I'm not going to go for too long today because I didn't prepare much. But this is why we choose the identity to be infinity, and also, in fact, if we have an elliptic curve of this form here, we can define kind of formulas for addition, so we don't have to do the geometric kind of line drawing every time. So we take, if we have 2 points p and q, and if either of them are the identity, then we do the obvious thing. If p is minus q, and this happens when y of p is minus y of q, then we give the identity here because p is the inverse of q. Otherwise, if p and q were the same, so if we doubling p, then we take lambda to be this. I'll explain what lambda is later, and otherwise we set lambda to be this. Well, this looks kind of familiar, right? This is the slope. This here is the slope of the line between p and q. So the line between p and q is given by this formula. This is the slope, and you just substitute this line into the original curve because we want to find the third point of intersection between those, and then take the inverse of that. So the third point of intersection will be this, except these are all plus signs in the y coordinate here, and then you take a minus of that to get p plus q. So minus p plus q would be the third point of intersection, and p plus q is this. Why we take lambda to be this in the first place? In the first case, well, we actually, if we're doubling p, we're taking the tangent at p. So we take a derivative. That's why we have a 3 out the front here. That comes from dropping the power of 3 in x cubed. You could do that yourself or something if you had some spare time during lockdown. I guess this is all right. And then so before I wanted to do things in a kind of a, well, we want Bezout's theorem to hold, right? So we want something where in Bezout's theorem we wanted projective curves over an algebraically closed field. Well, we actually want to consider Q, but Q is not algebraically closed. Well, actually, yeah, it's not algebraically closed. But if you look at these formulas here, these in fact, if you take 2 points, 2 rational points, so if xp and yp were both in the rational numbers and q, same with xq and yq, then our sum here, p plus q, is also a rational number because we aren't taking any square roots or anything. It's all just squaring and adding and multiplying here. So that means if we take points in q, we also end up in q. So that means, that means q, we can take elliptic curves over q, and that's interesting because then we get into kind of the cryptography side of things and that sort of stuff. Just a couple of more points to make is that any point of order 2, that means any point satisfying p equals 2p, which is not the identity, that only occurs if the point is on the y-axis, so yp is 0. And I claim that they're at most, I think that should be a 3, not a 2. And then if points of order 3 look like this here, so this is a condition for points of order 3. So I guess it's open discussion now. I kind of want to ask where we want to go with this reading group, whether we want to keep talking about elliptic curves. So if we do talk about elliptic curves, we can go to the Navier-Stokes theorem or the Mordell theorem or that sort of stuff. So the first theorem is giving a condition on when a point, a rational point, is of finite or infinite order. The second theorem tells us that it's finally generated. So we can, well, in fact, it's isomorphic to this thing, and we can do some kind of cool group theory things on that as well. So where do people want to go? I think, Oliver, you wanted to do a Dirichlet thingy, not Dirichlet, you wanted to do a, what was it?
I wanted to do a Fermat theorem next week, but if you guys want to do elliptic curves, I can head in that direction as well.
I think it would be nice if you did a bit of kind of that analytic stuff. So Fermat's, so let's.
It was algebraic more of.
Oh, algebraic, yeah. I think it'll be nice to do something else, so everyone can get a feel of what number theory is and that sort of stuff. And Samuel, you were okay doing something on cryptography, right? If you're here, I don't know. Thanks, Edward. Cryptography, classic. Okay, I'll let you and Samuel. Yeah, how about Edward? Do you want to talk about cryptography? I think you like that. Oh, classic. Okay. So Samuel can I guess talk about cryptography something. But so the 10th of April is Good Friday, and somehow I managed to book a room on campus for that. But we are still in lockdown then, so we will have to do something over Zoom. So will anyone be around on on Good Friday, or is everyone on break?
I think we're all around, right?
Yeah, we got literally nowhere to go.
Yeah, okay. I guess we could do something on Good Friday if enough people turn up. I will next meeting I will use the Auckland thing, so there isn't a annoying 40-minute thing, 40-minute deadline or whatever they call it. Yeah. Oh, Samuel and Lucas has been discussing a definition of projective space. Okay. I don't actually know the proper definition of a projective space. I just whipped something up from the notes I had before. It was the definition I found in Twitter.
Interest for you to say that there is one point in infinity, because you say it's a affine space plus a point at infinity. But
it shouldn't be point. If
it's a hyperplane at infinity. So,
Yeah. So if we were in R2 or
In
C2,
minus one dimensional.
it'll be 1 point. K in union.
I
infinity.
think
Wait,
in
what did I write?
2 dimensions you have a line at infinity.
yeah, Pn
Yeah.
space is An plus Pn minus 1 at infinity.
Yeah. Okay. Thanks. Yeah. Yeah. So it should be a line in infinity if this has dimension 2 or yeah. So this should be Pn minus 1. Okay. Yeah, that makes sense. Thanks. I will.
Yeah, but just making sure, like you still take the origin to be the point at infinity above the y-axis, if that makes sense.
Sorry, repeat that again, Oliver.
Like you know how you define the origin
Yeah.
to be the point at infinity. I guess you're taking it to be the point at infinity above the y-axis. If that makes sense.
Yeah. Well, I don't
Okay.
take the origin as the point of infinity. It corresponds to when the last coordinate is 0. So if we
Right,
do something
yeah.
like this,
Mm,
if we take it to point xy, if we look at this diagram here, so this is our plane R2, and we're kind of lifting up to a project space. So we go into R3, and then we consider the equivalence relationships of the lines here. And each line intersects the plane at exactly 1 point. That's the point that corresponds to a normal point, except when z is 0, which is down here. And that will be the point at infinity, basically.
Right,
So
okay.
And that diagram. I lifted this diagram straight from, I think, Reed's notes. So, yeah. If you wanted to see more about projected space, I guess look at Reed. Yep, I guess that's all for now. We're going to get kicked off Zoom in approximately 2 minutes. So, Oliver, yeah, it'll be great if you do something about Fermat's next week. I think that would be nice.
Sure. I'll see if I can, I'll figure out how to write stuff on my computer.
I think Kate had a fancy setup where you had a camera on top of a stand that you could do something like that.
I got a Surface, so hopefully I can write on it, but I'll see.
Oh, yeah. I have a drawing pad. Oh, let's turn my webcam back on. So I have this thing here. That's why I can write stuff. But if you have a Surface or a tablet or something, that would also work. Yeah.
Yeah, I made a stand that I could prop my phone on top of to like film what I was writing on the paper, but also I'm filming like 208 tutorials now, and I realized that I can just like blue tack paper to the wall and film that like it's like a whiteboard. So those are some DIY suggestions.
I think the quality of a video of like someone writing down might not be the best if you do it on Zoom. I don't know.
Yeah, even I think the resolution of me writing there wasn't absolutely clear, right?
It was actually alright.
Okay, that's good. What's Osu, Edward?
Osu. It's Os.
Is it? Oh, it's the okay.
I'm joking. It's Osu. It's a rhythm game where you tap around. You tap buttons. Yeah.
Classic. So is that what you're spending your quarantine, your isolation on, Edward? Right. Zoom's giving me warnings now about the time, so I think we can call that a day before. Yeah, Zoom's gonna kick us any minute.
All right.
now.
I'll see you guys later.
Okay, bye.
And I will send out an invite probably next Monday or something, and we can hear Oliver talk about Fermat's theorem.
Okay.
Cool.
Thank you.
Yeah.
Thank you.
Okay, cool. Thanks, Tristan. See you later.
Bye.
Bye, Tristan.
Oh, hi, Edward. Bye, Edward.
Oh, bye.
Bye-bye.
Thanks for hosting.
Bye. Thanks for coming.